Wow. Okay. All right, that's more than you needed. Thank you very much. Okay, this makes it a little easier, but sorry for the hassle. All right, first of all, let me say I have had a wonderful time here. Roland Allen, who set me up with a schedule that looked impossible, actually gave me a wonderful day with talking to your faculty and the things that go on here. This is a spectacular place. You ought to be very proud of it. I mean, I really learned a lot of interesting things, and they're not things you learn at MIT. So thank you for that, and thank you for having me. So I'm going to talk to you about what it says on the thing, and I may do something which is going to fail, because I want to do something because I know you people are technically competent. I want to go a little bit into how the detector actually works, rather than give you a long thing about all the history and so forth and so on. I want to show you how the detector works and gives you some ideas about how it might be made better. I will show you some of the things that gravitational wave astronomy has found, but the major thing I want to show you is really so you can imagine with us how you make these things operate, and also what might be the future if you understand how you could improve the detector. That's really what I'm trying to get to you. So let me start by, let's see if we can make this work. Good. All right, let me go back one. Yeah. Okay. First of all, I do have to say, look, this comes out of the Einstein theory that was developed in 1915, and that's the general theory of relativity. In 1916, Einstein did a perturbation calculation, which is a calculation with not the full strong field, and showed that you could have gravitational waves. And this was one of the things that's really quite distinguishing the general theory of relativity from Newton's theory. There was now a news function, a way of information in the gravitational field going from one place to another at a finite speed, not at infinite speed, like you would have interpreted if it was Newton. And this is what these waves look like. What they look like is, well, I'll get to that in this picture here, but first of all, the sources are accelerating masses, very much like an E&M, but they're not all kinds of motion. And in fact, in 1916, Einstein made a significant error in his first paper. In that paper, he in fact relates the motion of all sorts of things, including spherically symmetric accelerations, things that blow up and collapse like this. They radiate in that first paper, which is sort of completely wrong. But the rest of it he gets quite right. He gets the kinematics right, and this is what he does in that paper. He says that they are, he doesn't say non-spherically, but it is, now we know from the 1918 paper, it's non-spherically symmetric accelerating motions of masses. And the waves, they propagate at the speed of light, and they're transverse waves, and that's what this picture will show in a minute. These waves either coming out at you or going into the picture, and these dots, which are, you can think of masses that have been put into the field, and this red spot right there is you. Okay, so let me do this animation and turn it on. And then the reason I want you to understand this is then you will understand at least one aspect of how these detectors actually detect. In other words, what you see in this picture is that here's you, and you notice these spots. First of all, in one motion, let's say the x direction, something else is happening then in the y direction. Let's say it's stretching space in the x direction, it'll contract space in the y, and that flips. You can see that happening, of course. That push-pull aspect is very important for the detection. The other thing that's in this picture is that if you look at two spots that are near you, like these two, they don't move very much. But the ones that are far from you move a lot. Okay? So when you then analyze this, it's very much like when you pull a rubber band. If you make marks on the rubber band and pull it, and you'll notice that the motion that's with your hands is a lot, where that motion in the middle of the rubber band isn't very much. You're looking at a pattern of constant strain. Delta, the change in distance. Take the change in distance between this guy and that guy, and write it down, and then ask what's the separation between these two. The change in distance divided by their separation is a constant in that picture. Now, it's not constant in the sense that at any one instant it's a constant. And it's a negative value for one dimension and a positive value for the other. So the thing is that this is then the thing that's the basis for the detection, and I want to show you the detector. Okay, there had been ahead of this, there's this history I don't want to go into a lot. You can ask me about it at the end. But there's a guy, Joe Weber, who had thought he had seen gravitational waves. I'll just tell you right now why he didn't see anything, because his detectors were not sensitive enough to even get near the sensitivity and strain that's required. We'll get to what that is. So he was a factor of 1 million off, 1 million in strain sensitivity from where he could have detected something astrophysical. You'll see that in a minute. But the important thing here is this is a different technique which was invented by many different people. But the idea here is something that you are quite familiar with. So let me walk you through this. The basic idea is this, that here's a laser. You put light into a system which is a Michaelson Interferometer. There's a beam splitter, and then there's a distant mass, and then there's a distant mass. And imagine that gravitational wave that I just showed you coming down on the system. So this, let's say, is where the red square was. That's where you were standing, and nothing moving. Nothing was moving there. This was moving a lot in, let's say, moving toward you. This was moving away from you when that was moving toward you. And these are the far distant masses along the x and y direction. And now, what you do in your endeavor to do is you endeavor to make it so that the light time that's spent in here from the laser, the time it spends light in here is equal to the time it spends light going back and forth in here. In other words, this time going back and forth and that time going back and forth are equal. And the beam splitter has a positive sign and a negative sign. That means what happens on the positive sign when a wave gets reflected from the positive side, the electric field in the wave does not flip over. It just stays what it is. That's called the symmetric side of the beam splitter. On the other side, it's negative. We'll see why that's essential. You can't conserve energy without having that. And so here, what happens when something gets reflected from this, it turns out it flips the electric field. And so what happens when these two are the same, the times are the same, the electric field comes from the laser, there is no field at all to the photodetector. In other words, this is dark. Okay? That's the basis of the experiment. But I want to go one level deeper to talk with you about that. I don't normally do this. I want you to understand the next steps in this. And I want to show you, and I want to do something which may insult your intelligence, and I'll look at you and see if you say you're totally bored. Let me at least explain something about modulation to you. Yeah, I'm sure those of you who know a little bit of electrical engineering know this already, but let me, at the risk of making you upset, let me just give you some pictures. We can do it. This won't take that long. Suppose you have a wave that is constant. This is a carrier wave, and that carrier wave has got a constant frequency, okay? And there are many ways to represent that. You can represent it as a phasor, as you teach all of your undergraduates. That goes around at omega naught. That's the frequency of that wave, and that's the electric field of that constant field. If you had a spectrum analyzer, a device that looked at this frequency of each of the components of the electric field, you would get one spike on your spectrum when you look at it on the oscilloscope. So the red is the carrier, and you'll see that persists into the picture back into the... Now suppose you have amplitude modulation. In other words, here's what that wave looks like. It's the same frequency wave, but it has another wave that modulates its amplitude. That's this. It modulates it at a much lower frequency. And one way to represent that is as a picture that here's that same phasor again, and here are two sidebands, one at the frequency of the modulation and one at the negative frequency, below and above the carrier. But you notice what they're doing. When they oscillate, they tend to change the length of this vector. That's what they do. And this whole system is turning around at omega naught. Simultaneously, this is oscillating at omega m. These two things, they're moving in and out, causing the length of the spectrum to change. What's the spectrum look like for that? The spectrum for that looks like this. It's two sidebands, one below the carrier and another one above. And they're equal height, and they're equal in phase. In phase in the sense that they point in the same direction. Here's another kind of modulation. This is a modulation where you don't see the amplitude change, but you can see that the spacing isn't the same. You notice that the spacing gets a little narrower here, then it gets wide again, narrower. That's frequency modulation. That's phase modulation. And the modulation envelope for that, here is the carrier. And now what happens is these are the two sidebands, which we'll talk about in a minute, but what they tend to do is move in the rotating system. They tend to move this vector back sometimes, the carrier, and sometimes forward. That's why it doesn't change the length of the vector. So that's called phase modulation. I'm sorry to many of you who knew all of this, but it's absolutely critical that you know this because I'm going to be using this over and over again in the picture. So let me go back to the interferometer. And now let's do the analysis of what really is going on in this picture. When you have a gravitational wave coming down, imagine the gravitational wave being at omega m, and omega 0 being the carrier coming out of the laser. So and you'll notice I try to make it easier for you by noticing that there are purple arrows as well, which indicate the direction of motion of the light. So here, light is coming out of the laser, and all there is the carrier. Okay? It hits the beam splitter, and there it goes off to this mirror, and it still has only the carrier, but it's smaller a little bit because of the reflective, half the power is going this way, half the power is going that way. It hits this mirror, and suppose it does what those dots were doing in that representation of the plane gravitational wave. And this is moving back and forth at omega n. Well, here's what happens. There are now sidebands which are phase-modulated sidebands. Doppler shifted, one way to think of it. And one is, this is the carrier, and now there are two sidebands that depend on the amplitude of the carrier. So the more carrier you have, the bigger will be the sidebands. Okay? And the information about the gravitational wave is not in the carrier. It's in these sidebands. So now let's look what happens going the other direction. Going through the beam splitter, here is the beam. It's still not yet modulated. Hits this thing. But remember this guy, when this guy is moving out, this guy is moving in. So the phase modulation products are different. You'll notice that this was negative. That's the same color. That's the one, the high frequency one. Here is positive, and that's negative. So now these two come to this point. This one gets transmitted through here, but this guy gets reflected by that thing that has the negative side of the beam splitter. And now what happens is two things. The carrier has disappeared, okay, because the carrier was the same on both sides, there and there. And the five sidebands have doubled. So only the sidebands go to, and that means there's no light going to the photodetector except the phase-modulated sidebands of the carrier. And now if you want to detect them, you have to make an amplitude modulation. Now you leak a little bit of the carrier here. That's a detail. So what the important thing is, I'm going to come back to this later when we start talking about how the interferometers actually work. So I hope I haven't bored you, but this is an important detail. Okay? Okay. You happy? Oh, so far he says, okay, I'm in business. He says it, okay. All right. So, all right. So we go forward here. So let's get rid of this. And so along comes Kip Thorne back in about 1975. And he says, yeah, this is a fine idea, but if you really want to detect gravitational waves from an astrophysical source, you're going to have to use it to measure strains of the order of 10 to the minus 21. That's something we did guess at, but Kip had really done some reasonably and very beautiful work in the early days of this field, establishing what was the amount of strain that would be the case from any astrophysical source you could think of. And he came to the conclusion that you had to at least get to 10 to the minus 21. That's a very small number. Most people thought it was impossible to do. And by the way, that's 10 to the 6 times smaller than what Weber was able to do. Okay? So Weber could not have seen any gravitational waves, and we knew that. Nobody else saw them. Now, in a system that's 4 kilometers big, the thing that's measurable is always the delta L. And so you would like to know how big is delta L for a 4 kilometer long system. It's about 10 to the minus 18 meters. So let's put that into some sort of context. That's 1,000th the size of a nucleus, a proton. And that's the kind of measurement that was thrown at us by finally when reality was put to the calculations of what was possible. And so those put two challenges to us. In two places, a 10 to the 12 challenge. In other words, we had to do 10 to the 12 times better in measuring the position of things than the wavelength of light that was being used. The wavelength of light was 10 to the minus 6 meters. And you have to get to 10 minus 18. That says you have to somehow measure 10 to the 12 times smaller than the wavelength of light. That's the first challenge. Turns out that's part of why I explained the sidebands to you. That's all part of that story. It turns out that's not the most difficult part. The most difficult part is this part. You also had to make sure that the vibrations of the, that were imparted to those mirrors were smaller than 10 to the minus 12 of what the Earth normally has when it's shaking. You, even in Texas here, are shaking by a few times 10 to the minus 6, 10 to the minus 6 meters. This whole room is shaking from the oceans and the Gulf and everything. We see it every day. And human activity, you are shaking by 10 to the minus 6 meters. So you have to figure out a way of making the motion of those mirrors smaller by another factor of 10 to the 12. And that's actually the harder part. Okay. So here then is the interferometer that made the detection. And now I can walk you through this quickly and show you where this business of the modulation sidebands come in. The first, I'll do this 3 times. This is the first one. This is that same, now this is the full detector. What you're familiar with is this the laser. You were familiar with from the other picture, the beam splitter and the distant mirror and the distant mirror. Okay? So there's some mirrors that have been added to this. Let's start with these. These are partially reflecting mirrors. These are called Fabi Pro Interferometers. But what they effectively do in this picture, they let the light bounce back and forth 300 times or so, and it leaks out of this thing. It's reflected from this system. But you make it so that the time the light spends here is the same as you do here with the same kind of reflection system. And you make it so that the light spends the same time in both places. And you still have this situation. Let's not worry about that mirror for a moment. That when the photodetector, everything is set up, and this is the negative side of the splitter, you get no light to the photodetector. That's absolutely the way you set it up. Same thing. And now what you've done is you've multiplied the sidebands by the number of bounces in here. So the number of sidebands have gone up by about 300 amplitude. Okay? And you have another thing that you have to do yet. And that is, let's look at if no light is going here into the detector, where's the light going? The light is all coming back to the laser. That's where it's coming. I didn't tell you that in the first picture, but that's what's going on. If there's no light going to the photodetector, all the light is coming back here. And here's an invention had by both Ron Drever and Roland Schilling, who was part of the member of a German group that was really, as far as I'm concerned, way ahead of all of us. Way ahead of all of us in terms of understanding these interferometers. And I wish they had survived in the initial form they were. And so the idea was here is, if all the light is coming back here, that would make a mess of the laser. That's first of all. So what you do instead is you put another partially reflecting mirror here. And what that partially reflecting mirror does is it does the following. The light that comes out of the laser would be always reflected by it. So there would be light coming to the mirror, to this partial mirror, and reflected. But there's also light coming back from the beam splitter, almost all the light that went in. And it would come through this thing, and so there would be two beams. One that comes in the direction toward the laser from the beam splitter through this, and the other one that comes out of the laser is reflected by this. And you can make those two beams cancel interferometrically. So you make the position of that mirror and its transmission so that there is no light going back to the laser. And that's called a power recycling mirror. It's a very clever trick. And what that does is the following. It now takes, and since there are no sidebands here, the sidebands don't come here. All the sidebands are going this way. This doesn't affect any part of the interferometer except one thing. It makes believe that you have a bigger laser. So if you have 10 watts in this laser, you will have circulating in this little cavity, which consists of the beam splitter and the test masses, no light this way, all of that circulating in here. You might have 500 watts in here. And you might have something like 200 kilowatts in here. Okay? Well, it depends, how you do it. And so consequently, you have now done the following. You've taken that carrier and blown it up to an enormous amount, and the sidebands have come up along with it. And so that actually has solved the problem of the first factor of 10 to the 12. Now, what's this little mirror do? This mirror is, we're now beginning to use it. We did not use it in the initial interferometer. We're now beginning to use it. It's a more subtle mirror, but now that you know about sidebands, it isn't so subtle to you anymore. What it is this. You can tailor the response of the whole interferometer to gravitational waves by putting this partially reflecting mirror between the beam splitter and the photodetector. Because it takes those sidebands and sends them back into the interferometer, into the arms, not to the laser. It doesn't go back. It goes in here, and you can have another crack at putting more sidebands, bigger sidebands, and different phases onto the sidebands. And so that allows you to tailor the response of the interferometer, which is something which is very nice. You can, if you have a source that you'd like to look at more carefully, you can pick the right transmission for that mirror and the right place for that mirror, and you can make it so you have a narrow band if you want. You can do a lot of clever tricks, adjusting the spectral response of the interferometer to a gravitational wave. And we're using it in a very crude way just to, get a little more sensitivity right now, but that's going to be a big deal. That thing was invented by Brian Mears, who was a young postdoc in the Glasgow group, and then was promoted by Ron somewhat, Ron Drever. So that's the complete interferometer. Let me walk you quickly through the noise in this system. This is not this system. The thing that you have just seen is the detector that made the detection. The difference between the detector that made the detection and this is the first interferometer, big 4-kilometer interferometer. The only difference is that there are differences in the mechanical structure of the advanced detector, which I'll show you in a minute. But the big difference is that mirror in front of the detector, and it doesn't make that much difference. So I'm not giving you anything that doesn't work even here. But this is sort of the noise budget, and I want to walk you through a little bit of this, because this is important for you to understand in terms of what things have to be improved if you want to make things better. So here is this is frequency. So here, for example, is 100 hertz right there, and this is the strain, but now as a spectral density. It's a strain per bandwidth, the square root of bandwidth. So for example, if you want to recover the RMS strain, let's say at 100 right here, let's say you're about 10 to the minus 23, you multiply this noise curve, which let's say has this envelope, and let's say right around here someplace, you multiply it by the square root of 10, and you get an RMS value of about 10 to the minus 22. So this is a little 10 times better than 10 to the minus 21. This is a little better than what Kip asked for. in the very first, this is the first go-round. And so let's see what limits it. What limits it is, here's what we call the quantum noise. Get back to that with a vengeance in a few minutes, but this is the shot noise, or the rate at which you detect photons determined, but actually it's the phase noise in the radiation field. And then there's something which does not seem to be a big factor in this particular interferometer. It will become so in the later ones, that this is the radiation pressure fluctuation. So you have that are pushing the mirror around due to the fact that you have light coming from the laser, and the laser light has fluctuations in its amplitude. So here you're limited by phase fluctuations of light that come out of the laser, and here you're limited by radiation pressure fluctuations of the light that come out. But where you notice we're not limited by it. We're limited here by two other noises. This one, which is the thermal noise of the suspension. What is that? We suspend the mirrors by pendula, just like that thing you see out in the hall here, the Foucault pendulum. It's a little shorter than that, but it's you suspend the mirror. You can't attach it to the ground, as I told you. So this is the first defense in getting that factor of 10 to the 12 in ground noise reduction. It's not a very good one, as you can see. And also, that's this, I'm sorry. The first is this curve, the seismic curve. I'm sorry, I should have said that. But the mirrors are hung by pendula. That's true for both the seismic noise that gets through and also the suspension having thermal noise. And what that's due to is the fact that you're operating a pendulum at room temperature. You have vacuum that's good enough so it isn't the gas that's buffeting things around. It turns out it's the noise in the elasticity of the flexures in the pendulum that make this. I won't go into that unless you ask me questions. It's a quite subtle and complicated thing. But we'll see in a minute. That isn't the noise that's going to bother us for long. We have a new noise, that's thermal noise, which we have to solve. Okay, so here's then the envelope. Quantum noise for part of it, thermal noise because we have the pendula, and then insufficient amount of seismic isolation. Now let me show you a couple of other noise terms in here which are important. You have to get rid of, in the very long tubes that make up the 4 kilometers, you have to get rid of the gas. And that, if you don't do that, and if you only have a residual gas to 10 to the minus 6 torr in those tubes, you might have a line that this is the noise. Well, it's certainly below this, but we are going to be below that very quickly. So it turns out we made the system, the thing that's living both in Louisiana and in Hanford, and so did the Italians. That's when we get to that. They are designed so that we are 10 to the minus 9 torr, which is a reasonably good vacuum, even for high energy physics. It's not as good as the best high energy physics. That costs the money. Here's a noise which is absolutely critical. This noise right there is the reason why people invented LISA, which we'll talk to later. This is a noise which has not to do with this noise. It's getting, you notice it's getting worse and worse. The lower the frequency, it goes up as sort of 1 over f to the 8th. It's a fantastically steep, almost a delta function, a step function. And what that is a noise that you can do wonders about, and we'll see in a minute how you do that. You can do wonders with getting rid of the acceleration of the ground, accelerating the mirror. You have a lot of ways of fixing that. It's how cunning you are about it. But you have a wonderful reference. You have the framework of the fixed stars that you can refer yourself to. And that's what seismometers do. And instruments that measure motion, absolute motion with respect to the fixed stars. You can use those instruments to reduce the motion of your mirrors. We'll show you that in a minute. On the other hand, there's another piece of it that you can't do a damn thing about, which is the fact that if there's sound waves running in the ground, or there are sound waves running around in the atmosphere above you, the density fluctuations of those, of the atmosphere, and the density fluctuations in the ground. Actually, if this is the mirror, and you have a density fluctuation that's traveling along like that, the mirror will get pulled over by that density fluctuation. That's a Newtonian term, a gravitational gradient term. And that's what this curve is. And so it turns out that just gets devastating, and you can't do anything about it. You can't shield it. There's no way to shield gravity. I wish there were. And so what happens is that you're stuck, and we have some ideas about how to deal with this, but I will predict right here that we're not going to do anything much better than about sort of 5 hertz on the ground. 5 hertz is sort of here. This will dominate, as you see, in any kind of ground-based system, unless you make a system that tries to measure those density fluctuations, which is the direction that we've tried to go in. Okay, so let me show you the progress that was made on the very initial detector, the very first detector. And that is, this is time, each one of these curves as it goes down. This is the same. This is now position sensitivity. If you want to get H, you divide by 4,000. But this is the same frequency. Here's 100 hertz. And there was a tremendous amount of progress over something like 8 years with the initial detector. We eventually made it to the design sensitivity, which is this dashed line in here. And at that point, we stopped working on this, and we went back to the NSF and said, look, we would like to build another version of the detector that's inside the same envelope. And that was part of the initial plan of LIGO to begin with, an advanced detector. And because this worked so well as being pretty much accepted in a limited region here, really at design, and we had a clean non-detection of gravitation waves, we did not see anything. We were able to convince committees that we knew what we were doing and that maybe going the next step with ideas that we were able to explain to them, we tried to make a better detector. And that's the one that actually made the detection. So here are the steps that were used for that. And these all have to do with ground noise. And we did very little. In fact, we weren't able to do much about the interferometry. So what the big step was to, first of all, make a much better ground noise suspension system. And this is one thing that was provided. This is a multiple suspension system provided by the Glasgow group. What it is here's some springs. Imagine one end of these springs tied to the ground. Here's one pendulum. And that pendulum hangs from another, and that one hangs from another, this one hangs from another, and this is a precious mirror that you're trying to keep hanging from another. And you'll notice there's another chain of things hanging behind them. And so that you can have electrostatic forces between this recoil system and the actual mirrors. They're behind these things. So that you could push against a thing that was already pretty well isolated. And so this system gave a factor of 10 to the 8 in ground noise isolation in a certain frequency range. I won't describe this anywhere except to tell you that it exists, and if you're interested in it, you should talk to us, because it's something that might be useful to you as well. What this is this thing is an active vibration isolation system. I'll only describe it in words. I won't point to everything of it. Here you can see this pendulum system is hanging from it. And this thing is a device that is very much like the sound-canceling headphones that you have that you sometimes use in an airplane. You know, where you measure the sound field, you have a headphone, and the headphone then makes a field that's opposite to the one that's picked up by the microphone, and you reduce the noise to your ear. So the way this works is you have seismometers inside the system. There's two nested systems like that, and you have the seismometer, you measure the signal, and you push on the system with pushers so that to reduce the signal on the seismometer. You null the signal on the seismometer, and you do this twice, one stage after the other. And this is a way to get rid of low-frequency noise. And any of you who do microscopy or careful mapping or trying to do careful work with no noise might consider this. It's not cheap, but it's probably the only way we know how to get now building noise and all the noise down so that you're in a regime where, well, you're down in the level of about 10 to the minus 14, 10 to the minus 14 meters of motion. So it's at low frequencies. And here then is the noise budget for this system. And this is a system we're living with, and we'll get to that in a minute, but I want to show you something. This is again, the strain spectral density. Here's 100 hertz. And you'll notice that this is not where we're at yet, but we're very close to it. This purple curve is the quantum noise in that system, the radiation pressure here, and here the phase noise. And by the way, this is nothing more than the Heisenberg microscope that you all talk about in quantum theory, except we're not talking about electrons, we're talking about a big object that weighs 70 kilograms. That's what it is, okay? And and then here's the noise that right now is our big headache. We haven't hit it yet, as you see in a minute, but that's the thermal noise, and I'll just tell you where it is, and if you have ideas, I'd love to hear them. That's the noise that's associated with defining the surface of the mirror on top of the 50-layer optical coating that is very, very high reflectivity. You make layers, half wavelength layers, quarter wavelength layers, and they're all on top of each other. It turns out it's a messy system, and it has it's an amorphous system, and it has a lot of losses, and those losses make thermal noise. And that is, in fact, our limit right now. It's the thermal noise in the coatings. Imagine that. Okay, so yeah, let me take you to now, this is an important picture. This sort of tells you exactly where we are right now. And this is a curve with both things as well as we now have them, as well as things we project for the future. I'll get to that later. But right now, I just want to show you something that's rather important. Here is the Virgo detector, which is a detector in Italy, as it was running with us in the runs. We'll get to that. And they eventually made a discovery of a black hole with us. I'll show you that. Here is the performance, the actual performance of the advanced LIGO detector. And you'll notice something interesting in a second. There's that purple line. And here's where it should be, that green line. So that's this line. And you can see we're not there. At high frequencies, we don't have enough laser power. We couldn't get the laser power into it that we thought. And at low frequencies, we don't know exactly what the noise is. That makes the discrepancy, the purple line and the green line. Here is where Virgo hopes to be at some point. That's not, unless you ask me about that, I won't go into that. And these things I'll discuss later. These are things for the future. And in fact, these are still things that we think we can make in the current system. And then both Europeans and the Americans are thinking of detectors that are down here. And I'll describe a little about them at the end of the talk. Okay. So here is then what the distribution of detectors is. Here in the United States, we have one in Hanford, another one in Louisiana. The Italians have one near Pisa. There's a lovely research detector, which is the one that the German group has graduated into. That's called the Geo detector near Hanover. And there are two planned detectors that are going to be in the future. One in Japan called the Kago detector that's being built into a mountain, inside of a mountain. And this is another detector that comes from LIGO. We had a detector that was a half length of the full arms. And it turns out that was not a very good idea. And so we decided that we want to place that in another location, either Australia or into, it turns out, India. And it turns out the politics made it so it went to India. And these two, we hope, will be on the air in about the middle 20s, both of them. I'll tell you a little more about that in a second. Okay, so let me quickly, this is a quick tour of the site. This is the Louisiana site. And looking down on it, this is the same thing up at Hanford. These are the beam tubes. These are the concrete covers the tubes are inside of it. Here is the same thing in Louisiana. Now you could actually visit the Louisiana. It's very close to you. And here's a beam tube inside the culvert. Here's a laser table, like any laser table you have in your own labs here. And people working on it. And here's the control room for LIGO itself. And here are people learning from him how to operate the laser, how to operate the interferometer. So it's a fairly significant operation, the whole thing. Okay. So the first thing we detected, and the reason you've seen this 100 times, there are sweatshirts without, I even saw a lady who had this tattooed on her arm. I couldn't believe it. Who was at Harvard the other day. This waveform is the waveform that was I've seen at Hanford. This is time. That's strain. You can see the level of the strain, 10 to the minus 21. Not too far from the peaks on those values. But this is noise. This is at Hanford. This is at Livingston. And this is junk. This is junk. Too bad it's junk. There's some interesting signals there. But there is something that is superposed. If you superpose one on the other, you get this sort of picture which I have here. The one from Livingston and the one from Hanford. And it shows the critical importance of having two sites. And what is this is all noise. Noise. And if you it's been filtered to the extent of like what you might have in an audio set. You filtered the bass out. Here's a filter that was used, sort of. Low frequencies are cut, and the high frequencies are cut in the middle, that's it. And that's how much filtering there was done. This is just looking at directly there was a huge signal coming out of the detector. We didn't have to do any tremendous amount of signal processing to see this. And so what happened is that you then have a theory for if you make a theory about what it might be, we'll say in a minute what it is. We think it's two black holes, and you get waveforms that look like the signal, and then you can get the difference between the waveform, and this is the waveform predicted. That's the signal that you measured, and here's a residual from the two. That's one way of representing it. The other way to represent it is through a Fourier, just listening to it. In other words, here's time, same time as this, but now you say, what are the frequency components in that signal? Here's 32 hertz. This is about the bottom of where we are sensitive, and up to about middle C. And this thing is bright wherever the colors are bright. And it's much the same as given to the amount of the noise we have at the two sites. It's a bit of it's not worth listening to. It goes whoop, whoop, just like that. So it's a very simple little chirp. Okay? All right. This is what we think it was, and we're pretty sure of it. And by the way, there was another miracle, which you probably know very well in this, besides the technology all working. The other miracle is that we got the numerical relativists, the people who do from Einstein's field equations and use them and program them for a computer, finally succeeded in being able to actually take a black hole collision and actually make the signal that you see here. They were able to calculate the signal. That was absolutely critical to the interpretation of what we were seeing. And so it turns out that what this is now, without that bass treble filter, is what this thing should look like. This is time again. And what we're thinking this is two black holes, and we'll see what they are in a minute, getting closer, eventually getting very close, making a new black hole. And this lovely little ringing we didn't see. It says it's metric ringing. Once the event horizon forms, the metric itself oscillates for a while until everything stabilizes. And so that we didn't see, and we hope in other of these things to see it. And sort of the gee whiz part is that here's a one gee whiz part of it. And look at this green curve. This is the Green curve is the relative velocity between these two guys. And it starts at about 0.35, the velocity of light, and it winds up at 0.6, the velocity of light. Imagine things the size of 30 solar masses moving at like particles in particle physics. It's sort of unbelievable when you get to it. And so what we did, and this is now another way to project the same thing, very shortly after that, we saw more black holes. In other words, here's the event we were just talking about. And then here is the time again. And this is a very short event. This is the first one. Then there's another one we're not so sure of. This is, again, the strain on this side. Here's one we're very sure of. And here's another one which we just measured back in 1700. And there's another one we'll get to in a minute. But I just want to point out something to you. Here are the masses that are associated with the fits to this, to the numerical relativity things. 36 solar masses for one, 29 other, and 3 solar masses gets lost into the gravitational wave. Okay, now, it's an interesting thing which tells you how weak gravitational waves are. And that's this little calculation if you do it here, if you follow me. Suppose you took this that one, the big one, and stuck it at the distance to the sun. Okay, just put that thing at the distance to the sun. And this is what you would have measured. You would have measured a strain of about 10 to the minus 6. That means you would have measured nothing. I mean, your body changing it by a part in a million, you would not even notice it. You might hear it in your ear, just barely, because your ears are a good sensitive at thermal noise. But the power that went through you is just unbelievable. What went through you was 10 to the 25 watts per meter squared. And now what the sun puts out visibly is something like 1,000 watts per meter squared. This is 10 to the 22 times more than any electromagnetic thing the sun does. It's just unbelievable. It just tells you get very little squeezing of matter, a squeezing of space, by a huge amount of gravitational energy. And that's the reason why it's been so hard to do this. Okay. Now, you don't get, by the way, this is the position on the sky. This is a sky map of these various things. And you see that when you do this, you'll find out that we can't tell where we are, where the source is, to within about 1,000 square degrees. Why? How do you even tell any at all? You can tell where it comes from because it hits all of these things sort of hit Louisiana first. And the first one hit Louisiana first, went through the Earth, hit Hanford later, about 7 milliseconds later. And you can only get a little bit of position information out of that. And so so it turns out that's the reason why we're trying to get more detectors. And here's the first really big step forward in that. This is the same thing. There's nothing dramatic about this. This is now another source seen in last year in August 14th. And here is the LIGO, Hanford, there's the Livingston. But here is now the measurement that's seen in Virgo. And that was very important in reducing the error bar on the sky. For example, with just LIGO alone, you would have gotten a huge banana, still thousands of square degrees. And adding now Virgo to it, because you have another circle in the sky to get the timing differences, you can get down to something like 30 square degrees. And that's the way finally to get the attention of the astronomers. Go look there, okay? And we'll see how important that was in the next discovery. Okay, and this is the next discovery. And, well, I'm going to get into trouble. Oh, it's obvious. So, yeah, you and I are going to get into trouble. This is now the next discovery, which was a sort of big discovery back in also August of last year. What this is, I'm just not showing the time series because it was too small, but this is a much longer time series. There you can see it. It's a chirp that lasts for almost 10 seconds. And it's 2 neutron stars colliding with each other. And that was not just seen by LIGO. It was seen also by a gamma ray telescope, the Fermi gamma ray telescope. And you can see sort of 1.7 seconds after the end of the chirp, when these 2 neutron stars were close to hitting, they saw a burst. They saw a burst. They also saw another burst in another instrument on Fermi, and there was a second satellite that also saw something, but not as strongly as Fermi did. That was a real breakthrough, because what happened right after that is that here, it turns out that Virgo didn't see it, and we won't go into why. They were not sensitive enough, but they should have seen it, but it was in the null point of the angular distribution of the detector. So using that fact, you could get, here's the uncertainty in the sky of the LIGO alone, adding Virgo's non-detection to it, and here's Fermi's detection, and here's another instrument on Fermi which has a very huge packet. People were able to say, look, it has to be right about there. People with optical telescopes went to it, and they had looked at that region before, about 20 days before, and here's a galaxy. Here's some stars and stuff that were around it, and here's that new thing that they saw there. And that was the beginning of a really fantastic episode in astronomy. So seeing this now with a real telescope put a huge number of people into this. And in fact, I won't go into this slide except to say this is sort of all these marks say how all the different observations that were made over the next 2 weeks, and there were every conceivable form of electromagnetic observation was done. And here's sort of what they think this is. It's not completely accurate. This is changing daily still, what the model is. But the model is 2 neutron stars smashing into each other, making hopefully maybe a black hole, but that's what everybody guesses. And the gamma ray burst being a little off axis, so it's a little weaker. And this then spewing out a huge amount of nuclei and actually making a lot of heavy nuclei we'll get to in a second. So this was, and by the way, this is one of the things that I do want to predict for the future, is these people have looked for this. When these 2 neutron stars are going around each other, one of the things that is very interesting to everybody else, not also to us, is that the neutron stars will deform. They will, as they get closer and closer, tidal forces will separate them and change the period of their going around. And that's what's indicated here by them getting close. Here's a plot of, if you say, what's the quadrupole moment you induce in one star by the other, you can write that in terms of a constant times the second derivative of the potential, gravitational potential, and you can plot this in a sort of Bayesian way, and you can say, look, maybe this lambda isn't very big. It's sort of most of these things isn't near zero. But suppose you actually got a good measurement, you would see something like this. This is the period of the neutron stars like with each other, but you'll notice that the quadrupole makes it go a little faster, and so the waveform gets earlier and earlier, and until near the end. So you could, in principle, from the waveform itself, get the stiffness of nuclear matter, the equation of state of nuclear matter, which is a thing that's very heavily thought about by people. The other thing is that there was a prediction made, which is very interesting. And it says something we didn't know. This is new. That the people who now model, you can model black holes with the same programs as we've talked about, but you can also model neutron stars with those programs, and people have begun to do that. And now they can put matter in, which makes the problem exceedingly much harder, putting matter in, not just geometry. Geometry is the black hole. And you get, when the 2 stars come together, and they form something that is sort of a quasi-neutron star for a while, and it turns out that has normal mode oscillations. And depending on the equation of state of the material, you will get, depending on what, here are, for example, different kinds of things that you get for different equations of state. This is time, and this is amplitude, h. And here you can see sort of the overlay, and this is sort of advanced LIGO. This is the noise of advanced LIGO, and this might be sort of what, maybe we can see this. We maybe don't have to build the most spectacular detector in the world to see it. So these are for some of these sit way above, depending on the equation of state. So what we're going to do much more, and people are already doing it now, is look at the post-detection waveforms and see if they find high-frequency oscillations. These are all in the range from 1 to 4 kilohertz. Okay? So that's a very exciting prospect. This is now the other thing that has not to do so much with LIGO, but has to do with the astronomers. And here I'm somewhat disappointed, as I told one of your colleagues here. This is time in days, and this is the emission of that spot in the sky that the telescope found, and the colors indicate actually the colors of what wavelengths you're looking at. See some blue, and you'll notice something that they make a big fuss over. Maybe the blue light goes quickly down, the red light doesn't go down so quickly, and now there are models of this, which are complicated models. They never saw individual lines from this thing to establish that they were seeing heavy elements, but they are models of the opacity of heavy nuclei in a plasma. That's where this comes from Oak Ridge, and nobody can really get at that data, at least that I know. And they predict those curves, and those curves seem to fit this model of that all the heavy elements, not all, but a goodly number of them are made in neutron star collisions. In other words, here's a thing you can get right off the Wikipedia. This is the origin of the elements. I mean, here's, in the Big Bang, we have hydrogen and we have helium, and then and we got a little bit as far as lithium and beryllium, and then when the first calculations were done, people stopped here. You couldn't, from the Big Bang, get anything past boron. And all of this was later assigned, as you can see from the color coding, was assigned to supernova. So most of this stuff, that's middle masses, were made by supernova, and people didn't have a very good idea where the very heavy things, these purple things, come from. And now they think wherever it's purple, these things are the things that came out of neutron star collisions. And so here, for example, to entice the public, we have gold and platinum are made in these neutron star collisions and distribute themselves around the solar system, around the galaxy. So that was a big answer, maybe. I wish they had seen lines. The other thing is that this is a very cute idea, and in fact will be something for the future. And this is the idea that you can use these 2 neutron stars to do cosmology. And this was an idea that a lot of us have had. Bernie Schutz had this very early on. that if you have a system which you can calculate well from the Einstein field equations, you know exactly if you know the Einstein field equations are right, if you know the masses which you can solve for, then you can calculate the gravitational radiation at the source. And from that, if you have a good calibration of your measurement here, you could tell how far you are from the source. That's the idea, a real measurement of the distance you are from that source. And that was done. And what was done is that's the galaxy, which was the galaxy that was identified, where this neutron star merger took place, allowed you to get what's called the Z, the redshift of that galaxy. That gives you the amount of redshift associated with that place. You could then calculate the Hubble constant, which is the velocity versus redshift. The redshift versus distance. And it's a linear curve which allegedly fits the Einstein cosmological solutions. And here are two measurements of it. This is now the measure of the Hubble constant. And this is one measurement, is the measurement made by the cosmic background radiation, which through its structure, you get a number which is quite narrow. And here's a number made from the supernova searches. And they're also quite narrow number, and they don't quite overlap. People make a fuss about that. But here's the number, here's the curve that you get from this one measurement using the Einstein field equations and the neutron star masses. And you can see it's sort of between them. I don't know, it's very broad. But it shows the promise of this technique, which is going to be that has completely different systematic errors than the standard astronomy way of doing this. Okay, now I have to make a decision. I'll quickly tell you, there are many more sources to look for, and leave it at that. I want to go on, and I want to talk about the improvements to be made to the apparatus. As I told you already, there are two sources. The LIGO India and COGRA are the two that are coming, and what they will do is the following. You take a distribution in the sky. This is, again, a sky map. And if you have Hanford, forget about the second Harvard. That's Hanford, Livingston, and Virgo, which is what we have now. You get sort of uncertainty regions for a given signal noise, about 10 to 1, all over the sky. And now if you add to that LIGO India, you get something where now most of the uncertainty circles are sort of the size of the moon. It's a lot better. And that's one of the arguments for having multiple detectors, as I said earlier. And a lot of modeling has gone into that. The other thing I want to talk to you about is now the things that lie below where we are. Well, clearly, I already told you we have to make design sensitivity in LIGO, advanced LIGO, and we haven't done that yet. And we're busy trying to do that right now. And the thing is, then we have planned something called A+, which is also an improvement within the 4-kilometer system. And finally, an improvement, the last one we can make is Voyager, which is further improvements, and I'll describe some of those to you. And that's about as far as we can think now how we could improve the sensitivity by about a factor of 10 maybe over where we are relative to what the astrophysics is. It's a lot of astrophysics can be done. And I want to say something very important. The rate of events that we get depends on the cube of that sensitivity. It's not just, and where in astronomy, most things depend on the square root of the time, how long you can integrate. It turns out as long as you can think of ways to improve the detector, you always do better. Because what happens is this. Your sensitivity is equal to the distance that you can look at for the same event. But if you can look twice as far out, you're looking at a volume that's 8 times bigger of the universe. That as long as the sources are uniformly distributed, that'll stop after a while. But if they are, then you will get 8 times more events. So it goes to the cube. It goes to the volume of the space that you're able to look into. So that's a fantastic jump. And it's the reason why that happens is because we are sensitive to the amplitude of the signal, not the power in the signal. Okay? That's an important distinction. So, in other words, people here are now thinking, in Europe, they're thinking of burying a 10-kilometer triangle, 10-kilometer equilateral triangle. In the United States, we're thinking of somewhere in the world, since these will be international projects, of putting a 40-kilometer long L up. Not just one, but several, because you want to, again, be able to point. And those are way in the future. But those two things, if we do either one of those two things here, that takes this field and brings it into cosmology. Now, whether that's very important, and I've been trying to talk to some of your faculty about that, it will become important if it turns out that big systematic errors are different in the two techniques of looking. So don't throw it out yet. Okay, so here's the first of the improvements, and this is one of the reasons I showed the vectors, but I'm going to run out of time. I think it's worth, how many of you know about squeezing of light? I'm just curious. Oh, not very many. Oh, boy. Okay. Well, all right. I will do that and not say much more because we'll have to quit then. But this is a very lovely idea. This, by the way, and this is a very beautiful example of how the big shots in this field can get completely screwed up. For example, Kip Thorne and Ron Drever and I had this all wrong. And a young man named Carlton Caves comes along and he says, here's the way it really works. And what's he talking about is how that quantum noise that I told you about actually gets into the system. And it's very interesting what he came up with. What he came up with was the following. Here's a Michaelson Interferometer. Again, you'll probably recognize it. There's one mirror, there's another. Here's that beam splitter, and there's the plus and minus signs again. And you'll find out that here, for example, is this, so you have the same field. This is quickly a reminder. Here's the electric field, and here's an error circle that has both amplitude and phase modulated sidebands in it. So that's a little fuzzball you stick on the end of this. And it turns out that every noise that comes in from here doesn't do anything at the antisymmetric port. And you can see that in a minute. It turns out that all the noise that comes in that makes fluctuations in the quantum noise in the interferometer comes in from the antisymmetric port. And that's something we didn't really realize. And what it is the vacuum fluctuations that are in the mode of the radiation field inside the interferometer, which is determined by both the mirrors and the laser. That mode of spatial mode, the noise in that spatial mode is populated by the vacuum fluctuations that come in by the antisymmetric port. And you'll follow me through and you'll see. For example, let's look at, here's a vacuum fluctuation. We don't know where the arrow points at this moment, but let's sit somewhere. Watch it come in. It goes in, comes in here, it gets flipped over, and then, okay, eventually comes out again. But then look at this, what happens up here. It comes here, nothing gets flipped over, it comes back, and it has the same sign. So it turns out the vacuum fluctuation from here does get into the system, and it comes out again with this arrow. It does not do that on this side. A vacuum fluctuation in here gets canceled. It goes this way, and then it comes back, it gets canceled, you don't get it out. And so it turns out that, and that's true whether you're dealing with phase fluctuations or amplitude fluctuations. Here, for example, you can see it for the amplitude fluctuation. This is the coherent light is the red, and here's the incoherent coming in the A port, the antisymmetric port, the incoherent part that comes in the symmetric port, and this is the square of all of those makes the radiation pressure. On this mirror, it's the square of all these, again, but with the minus signs in the appropriate places. And it turns out when you take the motion that these two things cause, you get a change. The force is proportional to the incoherent light that's coming in at the A terminal, but not at the B terminal, not at the antisymmetric port, not the symmetric port. So this thing then is the thing that makes the radiation pressure noise. It's also the thing that makes the phase fluctuations, and they come in that support. So if you can do something, and this is the idea of squeezing, in one of these interferometers, if you could somehow convert this into something which doesn't have a fluctuation on it, you could then reduce the noise in the interferometer. And this is what the idea is, and here's what's tried. I'll show you the squeezing scheme in a second. But let me just say what it did. This was done both in the German detector, and you'll see that this is the curve without squeezing, the red curve. This is now frequency, again, strain. And you'll see that they put in what's called 3 dB of squeezing, which comes about by having done a trick which I haven't described yet, but I will. And they see a reduction, and this was only phase noise squeezing. So you can see that, but then they couldn't tell what was going on in here. Then the LIGO people tried this also at the end of the first run, and this wasn't as much, we didn't do as well, but they were very important to prove that it didn't make matters worse down in here. We were worried about that. So squeezing, the idea of squeezing then is the following. And here's sort of a picture which describes the whole thing. Well, the way you do it is you want to keep the antisymmetric. Here's again an interferometer, primitive, but this one has cavities, and here's the signal recycling mirror. But now let's go to this important place. What you do is and what's going on in this nonlinear device right here is you get green light, you make green light out of the light that comes out of here. So light that is equivalently in energy to twice the energy of the light that's running around in the interferometer. And you put it into a nonlinear optical device that does the following. It takes, and one way of thinking of this, it does the following. It takes the radiation pressure fluctuation, the field fluctuation that come from the vacuum fluctuation, induces a new photon to be emitted by this thing, and another photon, because remember it's twice frequency that's coming in that's driving it. But you make it so they have opposite sidebands if you want to make phase noise reduction. Opposite sidebands, these two photons. You can organize their sidebands together. So either they are amplitude modulated sidebands or phase modulated sidebands. It's how you set up. And so, for example, if you're smart, and this is an idea that Kimball had, and I think you may have had too at one time in your life, is the idea if you take the light that is now correlated, or call them entangled photons in the infrared, and let them reflect from a cavity, you can make it so that at low frequencies, the uncertainty will be all in the amplitude. So it will push the mirror around, but that doesn't matter at high frequencies. The phase noise is what matters at high frequencies. And then if you let that reflection be in the right place, like this is the reflection response, and these are the error circles, this is all phase modulation. No, this is all, well, it becomes, the thing that's left, you're squeezing in the phase quadrature, okay. And it just happens to be the other way around, the phase quadrature. And here you're squeezing in the amplitude quadrature. This is at low frequencies where you would get radiation pressure, and there's that benefit that you get even over the whole frequency band. And here it is. This is now, the quantum noise is the purple line, and this is without any squeezing. And this is with dual frequency squeezing, or the frequency dependent squeezing, and you get a nice reduction all around. And here is that awful noise still from the thermal noise in the coating. And you've got to do something about that as well. Otherwise, we're not going to get a big win-win big. So that's a very important issue. But the idea of frequency-dependent squeezing is adopted for, in fact, independent squeezing is going into the current next interferometer, the one we're going to be running sometime by the end of this year. And frequency-dependent squeezing is going to go into something called A+. And so this is one of the big developments. The other big development is, oh boy, yeah, I knew this would happen. The other development, I'll just tell you what it is. I'm not going to devour Sky because I have to get out of here, and she's getting nervous. Is that we were not able to put all the power into the interferometer we wanted for a very complicated but straightforward reason that Vladimir Brzezinski pointed out to us. And the idea is this, given in this picture. It turns out that if you hear mechanical modes of the mirror, these mirrors, and if you send light on the mirror and you have scattered light, the scattered light will have some kind of pattern. If that pattern overlaps the radiation field pattern of a cavity, you can excite those modes, the optical modes in that cavity, mechanically. And so, in fact, that's what we found. We found that as you increase the power, you get a parametric conversion that makes it so the mirror starts shaking like crazy at 15 kilohertz. Okay, because the radiation pressure fluctuations are driving the mirror to oscillate, and then it destroys the wavefront. So we were not able to get up to megawatts in the cavity. We only were able to get 200 kilowatts in the cavity. Now we know we can get up to a megawatt by putting little dampers on it. These are little dampers that don't make noise at low frequencies and actually kill the modes at high frequencies. That's just a step. Okay, so let me just finish by saying this is then the field, this is frequency, and these are other things that are going on in the field. This is now strain. Here's LIGO. I've said a lot to you about it. That's all high frequency, but there's the LISA project, which is low frequency, up to sort of minutes to hours, and that's 3 satellites. And this is a 3 satellites in Earth orbit, in the Earth's orbit around the sun, and that will look at low frequency gravitational waves, particular massive black holes, sort of 10 to the 5, 10 to the 6 solar masses going into each other, small black holes going into a big black hole, and measure actually the white dwarf binaries in our own galaxy. This is a big project hoping to go in 2031, 2, 3, somewhere like that. The Europeans now are running it. It's a shame, and the Americans gave that away. So this is then another one, which is pulsar timing. This is using the fact that you have many, many pulsars, millisecond pulsars, and if you watch a gravitational wave come through our galaxy, and you look at, again, pulsars up there, and pulsars down here, these all will slow down in their rates, and the ones east-west, they will speed up in their rates. It'll be a very pretty thing to watch. And you can see the gravitational waves coming through this galaxy. If you're looking for gravitational waves with very, very long periods, decades to halves of years. And then finally, there's this thing which is the B modes, which are the modes of polarization of the cosmic background, which I won't describe anymore to say that people thought they saw something. That experiment's going to work. If it has it, it'll be working in the next few years, and it will have more channels than one because dust will be taken care of. Let me put it at that. Thank you. Yeah.
Are you taking questions?
What?
Are you taking questions?
Yeah, sure. You want to get out of here in 5 minutes. Okay, I'd love to have questions, but I'm under duress because of that. Okay, I'm sorry about that. Yeah. My wife is sick and I have to get home. That's fundamentally what the problem is. And so, yeah, go ahead. Speak up though, because I.
Your sensitivity goes down pretty quickly with low frequencies, but your future generation looks like it doesn't go down.
Yeah.
What's the big difference?
The big difference is the big difference now is that we hope to get rid of the, most important thing is we're going to probably go to crystalline coatings if we have to. That's part of that curve is going up as low. The other thing is the squeezing will get rid of the momentum noise. We're now going to be troubled by the momentum noise, the radiation pressure noise. So it's, and we have such good ground noise isolation because we did that with that active system. We're not troubled by that from there. So we're beginning to see really fundamental noises. Yeah, wow.
One of the things that we used to look at was squeezing stroboscopically.
Yeah.
So I have a wave packet here, Gaussian, that defines the ends of my Fabi Pro or my Weaver bar. If I squeeze such that I start with a delta function, plane wave delta function, I can really do some good. Would that help your Fabi?
It might. We're not thinking about it because it doesn't fit into the geometry. That's the real problem, yeah. But right now it looks like the squeezing has worked both for the Germans. We're really following the lead of the German group who has done it in their 600 meter and the Australian group which has done a lot of the work in making the OPO and making the doubler and everything work. So we're going to, look, it's all gifts to us. We don't have to do it ourselves, you see. Yeah. Any other questions? Yeah.
So this Brownian motion limit that you mentioned is really the first time I've ever heard of that.
Uh-huh.
Is there a lever to crank on that problem to try and improve that?
Yes, there is, but there are many, that's a long topic. The way we will be fighting it is by something called using the fluctuation dissipation theorem, which you've probably learned in some statistical mechanics course. And when I learned about it, it went right over my head and I didn't care about it. But now that I'm in this business, it's very, very important. What it is that thing which brings in the thing that does the dissipation of a mechanical system, that takes the energy out of it, is exactly the same thing that brings in the fluctuations. And that, for example, a simple example of that is just particles in a poor vacuum. They will damp the system with viscous damping, but they also put in the fact that the thing shakes. And so it turns out that's going on in the solids, it's going on everywhere. If you have a dissipation, you can guarantee that you know the fluctuations. And what you have to do is improve making the fluctuations, making the dissipation smaller and smaller, and we're working on that. So the other way is if you really have to do it, and you need to do it, you have to cool. And you gain slowly with that. You only gain with the square root of the temperature. But people are doing that. The Japanese, for example, are going to cool their system. And look, it's a bitch to think that here is 1 megawatt on fine threads, and you're going to take the heat out of that mirror. Ooh, you know. Yeah, well, you know, it's a challenge to do the cryogenics. Yeah. Anything else? Yeah.
Did you consider frequency comps?
Say again, please.
Did you consider frequency comps instead of monochromatic laser? Purely FM comp.
Yeah, I know about them, but I don't know how that helps anything.
You like dual comp spectroscopy, I would guess, if you actually combine one on top of another, and they have a very high phase stability, and you could translate it from optical to radio frequencies. It's like absolute ruler. I'm just guessing.
Yeah, I'm trying to figure out how that helps us. Let me think about that, okay? It's not obvious to me that helps. The CW is so damn important in terms of a lot.
Intensity will be stable.
It's not that. It's the CW in terms of the modes that you excite and all sorts of other stuff. Look, let me stew about it. I know what you're talking about. I mean, I know people have made wonderful clocks out of that. That's true. Yeah. Anything else? Wow. Well, thank you very much. Yeah. Yeah.
Good job.
Yeah.
Thank you for coming.
Yeah, no, thank you for having me. Now, thank you for this. Look at that. You gave me another one. My name
So
on
are
it.
you at LSU part of the
Oh, yeah. I come by. I haven't been traveling to LSU lately because I've been in this stupid Nobel Prize thing. I shouldn't say this so loud, but
Well, if you're going to be over there, let us
it's
have
not
a
that
shot
far.
at
It's
you,
not that far.
It's not that far. That's the best talk I've heard in the 47 years I've been
Oh,
here.
go on. Don't give me that.
No.
That's Schmeich.